Hey guys, my name is Daniel, and today I'm going to be presenting River, the homemade programming language that I've been working on. So as an outline of this presentation, first I'll talk about what this language is, I'll talk about why I made it, show an example program to render the Mandelbrot set, give a timeline of the language's development and conception, an overview of its design, talk about some of the challenges that I faced, and finally give some ideas for what my next language might include. So first of all, just basically, what is this? So River is a prototype or experimental compiled programming language. Um, it doesn't really set out to solve any challenges that exist in any existing languages, which I'll talk about kind of in the next slide. But it was really just designed as a method for experimentation. Finally, it includes an accompanying IDE, so you can write and test your own programs in an actual graphical environment. Why did I make this in the first place? The main goal was just to teach myself more about compilers and language design. It does not solve or address any problems that I face in any existing languages. So, I'm not going out here trying to take over C++ or Python with some crazy new invention. Um, but like as Linus Torvalds said, like 30 years ago, it's not really designed to be like a big professional thing yet. Also, I mean, I do see this as a huge nerd flex, creating your own programming language, but that was not the reason that I set out to create this. So here's an overview of kind of what the IDE looks like and running an example program. I'm gonna probably shy away from going too in depth on the syntax in this video because there is already documentation on how all the syntax works, and you can jump into the README and the documentation on GitHub. But sort of as like a basic overview of the IDE, in the top left hand here we have the source code. The source code is compiled into the bytes that we see here on the top right, and then the bytes are executed by a bytecode interpreter to create the output, which is in the bottom left quadrant. And then finally, this bottom right here, this is compiler debug information. So this is sort of useful for figuring out why the compiler is not behaving in the way that you expect it to. Yeah, and if you want to pause and take a close look here, this is the source code for the Mandelbrot set function. And I just want to point out, if you look at some of the mathematics, the syntax is pretty wacky. And the reason that it's built this way is not, as I said, not to solve any problems. I did sort of create my own notation for doing arithmetic, but this was just sort of to force me to differentiate myself a little bit from the existing languages. And when I designed this thing, to prove to myself that I did like create something new and I had properly applied the concepts. Yeah. And as we can see down here, it does render a pretty nice looking Mandelbrot fraction. So yeah, it works. So kind of as a timeline of the development, back in like 2014, I started programming on this, what you see right here, the Texas Instrument Calculator. It had kind of a very basic, it was actually basic programming language built into it. And I learned basically how to program on this thing. So in 2016, when I was in high school, I created kind of a simple bytecode language. So this is where you would make like an array of instructions and numbers, and it would iterate over the array, executing instructions, and then it would give you like some output at the end, kind of like maybe like a Turing tape, maybe slightly more capable than a Turing tape. So one of the programs that I wrote for this was like a simple program to calculate pi using the Leibniz summation algorithm. But at the time, I didn't really have any knowledge of like assembly code or programming languages, and my bytecode only had some very basic operations, such as like jumps and arithmetic and stuff like that. So and also had a fixed 64 byte heap that also served as the executable instruction space. So yeah, not like super sophisticated, but this was a good way for me to kind of get the ball rolling on programming language design. One of the other things that was a big headache about making this is how tedious it is to write programs. I mean, basically, I would write everything out on like notebook paper or graph paper. I would just draw out the entire like heap space and write my programs in that, manually like counting pointers and stuff. Yeah, it was not very easy to write programs in this language. So then in 2018, I started college, studying computer science, unsurprisingly, and I converted the aforementioned program into C++. So this would kind of give it a little bit of a speed boost. I had the same program to calculate pi, but it had the same problems of reading and writing in this bytecode is just such a tedious operation, and I didn't know how I was going to make it better. So kind of rolling around to 2019, I decided that I wanted to, at the very least, make a way to write the bytecode in text and then compile that text, down to the bytecode. So this is not as good as like a truly compiled language with all of the nice things like for loops and functions and stuff like that, but it would at least allow me to avoid having to think about like, where my pointers were located and stuff like that. But this is not, this would then become kind of the more fully fledged programming language that I'm talking about today, where we have a defined standard and we have for loops and if loops, if else, and kind of nested arithmetic and stuff like that. So it was a gradual build up from a simple bytecode language to actually making a compiler. I did not start from nothing, just going straight to compiler world. We started from bytecode, and that sort of will come visible in the next few slides as I discuss kind of why I chose a lot of the design choices. It just sort of gradually came out that way. So next, sorry, my camera's in the way here, but I will talk about programming language design philosophies, and just sort of basically, people teach entire classes and have written like entire textbooks and dissertations on this kind of stuff. So this is the five bullet point summary of all of that. But in summary, there are three different types of like programming languages, or one of the ways to categorize the programming languages is this. So you have your interpreted languages, which is where the source code is read line by line, and every line that the interpreter reads, it executes in real time. So an example of this would be like Python or like JavaScript or BASIC. And one of the advantages of this is it's very easy to write interpreted code, but the disadvantage is, one, it's generally like slower than the alternatives, and secondly, you don't always know that there are issues with your code until you run into the issue. So other types of languages will tell you that there's an issue before you run your code, which is good. But yeah, interpreted languages. Second of all, we have bytecode languages. This is where your source code is compiled into like a sequence of bytes, which are sort of like basic instructions, but it's not the same as assembly code. It's more proprietary. And so examples of that would be like Java and Lua. So there's like the JVM, which interprets compiled Java bytecode. And then lastly, we have truly compiled code, which is where the source code that you write is directly compiled into assembly code or assembly instructions like x86 or ARM or something like that. And so many languages like that are very popular, including C++, Rust, C, and several others. So the big asterisk here is that in practice, a lot of these languages can fall into like multiple of these categories. Just as like an example, in Python, there are ways to like compile Python code into instructions or like use JIT compiled. So there are like exceptions and overlap between these different groups, but in general, this is like some of the three main like design philosophies. Put my camera back up here. So this is a bytecode interpreted language. Why did we decide to do that? I think that like for interpreted and compiled languages, some of the benefits are really obvious and some of the design choices are really obvious, but bytecode is one of those like weird gray areas to me. So the main answer that I have to this question is I didn't know assembly when I wrote this program, and the first version of the like basic instruction set that I was using was not written in assembly, it was written in C++. So it was easier, like the natural progression of me making this language was to compile to the bytecode instructions that were then interpreted in the C++ program. So this really is like a compiler on top of a previous bytecode specification that I wrote. If there is a silver lining to this at all, it's that it's architecture agnostic. So I mean, like a program that you write on a 64-bit machine could work on like an ARM machine or something like that. But that is like maybe not as big of a benefit as it sounds. Finally, it was just much easier for me to create this than going straight to compiled. However, I think in the future I would want to just eliminate the bytecode and go straight to making a compiled language, because that just seems to make more sense in today. Yeah, so obviously creating something like this was very challenging. I experienced several challenges, and I want to just kind of talk about some of the ones that I was able to solve, and also some of the ones that are still outstanding and might become things I want to solve in like a next version of a language if I make one. So the first one that immediately was like the first thing that I had to deal with was multi-operand arithmetic. So in assembly, if you want to add like two numbers together, it's pretty easy. Most processors have an instruction to add two different memory addresses together, no big deal. But if you want to do something like this, where you're like running 5 different arithmetic operations and they're all really complicated, and you need to like chain them up and then store them in a final pointer that is then remembered by the compiler for the rest of the execution time, it's not just one instruction. It's going to be like a lot more. It's going to be like 20 or 30 instructions. Maybe not that much, but it's going to be several instructions. So we had to teach the computer how to do the order of operations, how to know which of these needs to get run first, and then managing the memory to handle the results of this operation. So 7 plus 8 is going to get stored somewhere, and then that value is going to get exponented with 6. Exponented, I don't know if that's a word, but and then this is going to get run, and then that's going to go to a memory address, and then this is going to get run, and that's going to go to memory address, and then those two results are going to get multiplied together, finally getting stored in the location of heap space that we allocate for memory address A. So yeah, the compiler has to know kind of the sequence of kind of like abstractly for all legal math operations, how do we chain them up the right way? So that was the first thing that I think was really challenging. And also one of the things that compilers do that we take for granted. The second thing was control flow logic. So things like for loops, if-else statements, and while loops. So if we want to do like conditionals in assembly, that's pretty simple. There's like the jump if 0 command. So if a certain value is equal to 0, then we continue. Otherwise, we jump to a specific like instruction in memory. But when we compile this, we do have to be cognizant of where in the actual compiled code each component of the for loop goes, and also where our memory pointers are. So maybe that sounds a little bit agnostic, but I'm going to try to clear that up. So here's like an example of a for loop in C++. As we can see here, like the for loop has these 3 arguments when we create it. So when that actually gets converted into like the basic instructions, the first thing we do is we execute this before anything else of the for loop. Then we have our sort of jump conditional. So that's if I is greater than 10, then we jump to whatever's after like the code section of our for loop. And then finally what runs after each increment of our for loop. And so that gets sort of rolled out into this sort of pseudo assembly code. But the one thing that I thought that I did find challenging was, how does your compiler know where to go, like where you have to jump to when the condition is met? Because we know that like when the for loop is done executing, we jump to the end, but how does the compiler know how many instructions are going to be inside of the for loop? And so that meant that we had to start keeping track of sort of like, we had to make like a placeholder value for this, and then we had to say, now we calculate how many instructions are inside of here, and then once that's done, then we fill in this placeholder value. Yeah, so those are two of the challenges that I solved. One of the things that I still have not really figured out yet is memory management. So we do have a fixed sized heap, but what happens if we want to allocate more objects than what fits in our fixed size heap? Um, Another thing is like garbage collection. So if we allocate a variable and then we use it one time, why does it need to continue to exist in memory for the rest of the program execution time? Many modern programming languages that we use today are garbage collected, and a lot of people coming out of school don't really know or think about the memory management that actually like happens under the hood, including me. I don't really know a whole lot about. I don't have to think a lot about that. So questions such as like, how does a program know where in memory our variable can be allocated legally? When is it okay to free up that space? And then when we start program execution, how much memory do we need to reserve from the operating system at runtime? So assembly programs do not actually manage memory themselves, so it's up to the compiler to implement the method of memory management. Okay, another challenge, extensibility. So, we have our sort of simple conditional logic and variables in our language, but what if we wanted to add something like more interesting, like networking or like graphics? So one trivial way that we could do this is by just creating sort of like networking instructions in the bytecode interpreter. But I do feel like this is a little bit of a cop-out, and it's not sustainable if we want to continue to adopt and evolve with like new technologies. So adding new features, adding new libraries and stuff is going to be something that most modern languages support, and it's something that we're going to have to add if we want it to actually be like a real language. Another one, obviously, types. So the only type that we support in this language is a double type, but if we wanted to make more interesting things, we would need to have strings and lists and maps and stuff like that. And that's not even including like object-oriented classes and stuff. That's a whole another level. Yeah. So those are just some of the challenges, some of the solved ones, and also some of the unsolved ones. But yeah, let's talk about ideas for the next language. I do think sometime in the next few years, I'd like to try and implement a more real usable language that could be implemented as like a component of projects. And some of the things that I think I'd have to do with this design to get there, first of all, getting rid of bytecode. There's really no point in having bytecode. It has all the inconvenience of compiled languages, but it does not have all the full benefits. So you don't really get all the speed benefits because a interpreter still has to read your bytecode. So I think the next version would either just go straight to an interpreted language or straight to like assembly. I think assembly would be better, honestly. Second of all, and I'm sort of repeating myself, supporting like basic types and data structures, strings, lists, maps, booleans. If you are not considering functions a type, these would be sort of like the basic of the basics that I would expect in a real usable programming language. Third, support for functions and stack frames. So it does have currently support for like goto and flags, which is why I do think this is like a little bit lower of a priority. But most people are used to like functional programming, and I think it would probably just be a good idea to get rid of like the gotos, especially if we want to have like variable scope and stuff like that. Fourth, smarter memory management. As I said, growing the heap size as variables get bigger, and also the stack. But I would think maybe not worrying about garbage collection at the beginning, just because that is very complicated. Maybe in the very basic we could do like something like ref counting, but garbage collection would be a much further in the future feature, in my opinion. Okay, I think this is probably the most important thing that I would have as a goal, which is to write a compiler in itself. The two reasons for this: one is like you have to eat your own dog food, so to know that your programming language is good, you have to use it. And what better way to use it than to write the compiler in itself? I also think this is a good litmus test for proving that your language is like actually good or not. If you can write a compiler in your own language, then it's good enough to use in real projects. Maybe. Huge asterisk there. Don't quote me on that. Lastly, not lastly, extensibility with other libraries. So I'd like to have a way to incorporate new features rather than just building them into the compiler. And so one idea that I had was maybe the way to link C and C++ libraries into the project. I think that would be good because C and C++ obviously have like a very robust ecosystem. And so then we would get automatically a huge amount of extensibility. And then finally, improved I/O. So I do have some very basic bitmap graphics, but I think if you want to create stuff like games, especially, or useful programs that have input and output, because right now all you have is kind of just output. Ways to like print all the data types, for instance, taking in keyboard input, and also improving the graphics. So like rather than bitmap graphics, maybe some way to do communicate with the GPU or something like that would be good. And maybe these could be implemented as libraries, because I know that in like C++ they're implemented as libraries. So maybe that's the way to go. So yeah, in conclusion, this has been a very long project that I've been working. I mean, on this code base I've been working on for almost 5 years. So I did learn a lot. It's still a lot of holes in my knowledge. But a lot of those things that I have question marks about, I think could be just ideas for future iterations of the language. And yeah, I'm very interested if anyone's reading this and knows about these sort of projects. I'm interested in your feedback, your suggestions. And in the video description here, I'll have a link to the GitHub repository and also a link to the online IDE where you can test and write your own programs. So thank you very much if you've watched to the end of this video. I really appreciate your time. And I hope that you find this sort of thing interesting, and leave a comment if you have any ideas for how this could be better. So thanks a lot, and I'll see you guys in the next video. Bye-bye.